When digitizing information, there's always a loss of information to make it fit the digital format we use. What if there was a way to eliminate that loss? And here to talk about that possibility from the Weizmann Institute of Science, Yonina, Eldar.
Thank you so much, and thanks for that really nice introduction. So good afternoon or morning if there's anyone from the US. It's really an honor and a privilege to have this opportunity. So I'd really like to thank the organizers for the invitation and for accommodating all the technical issues as well. So I'm really happy to be here and to have this opportunity to share some ideas with you that we've been working on, and of course many other people are working on, where really what we want to look at kind of the half an hour that we have is how we could couple physics together with algorithms in order to try to overcome basic bounds that limit the technology that we develop today. So we'll see that this paves the way to what we've been referring to as pace tech, which we'll show could be faster, consume less power, be smaller and more portable, and have higher resolution than many existing digital devices. And we'll try to show throughout the time we have both the theory behind it, but also a range of applications, from optical imaging, medical imaging, radar communication, and more, as much as time will let us do. So what we're talking about here today and in general, of course, within this conference is, digital data. We're part of the digital revolution where more and more processing is being done in the digital domain. But of course, if we want to be able to digitally process analog data or true physical signals, then, we have to first digitize it and then do our processing and project it back to the analog domain. Analog girl in a digital world. So that always hopefully serves the purpose of waking everybody up. So this really cool song by Judy Gorman, which I strongly encourage to go ahead and listen to all the words. She sings about being an analog girl in a digital world. And this actually really nicely captures this essence of digitization or sampling. So at the end of the day, we're doing everything in the digital domain by digital processing. But in order to do that, we have to first convert our signal to the digital domain. And that is typically done in two stages. We first sample the signal at certain points in time, and then we digitize the samples that we took. And today, essentially all analog to digital converters work at the well-known Shannon Nyquist rate, and that ensures that we could kind of faithfully represent the signal in the digital domain. So just to get a sense of where these theorems come from and why we need them, suppose we have some physical signal that we want to process, and all we're given are the samples. So we're basically just given the blue dots. We don't actually know the red curve, and we want to be able to recover it. So of course, the original signal will fit our dots, but there's many other signals that will fit our dots as well. So the question is, of course, what is the correct one? How do we preserve the information? And one way to ensure that we're preserving the information is to limit the speed of change. So you'll notice that our true signal is much slower than these other signals that fit the samples, but they're not the correct signals. So this intuition is really the essence behind the famous Shannon-Nyquist theorem, which says that if you want to faithfully represent the data, then you have to sample it at twice the highest frequency in the signal. Okay, so that's kind of the essence of the Nyquist theorem. And together with the Nyquist theorem, another important set of results are the results by Shannon, the father of information theory, who developed a really important and beautiful mathematical theory to describe how much information we could convey, let's say, from a transmitter to a receiver in a communication context, and also what's known as rate distortion bounds, which tell us how many bits we need to represent a given signal. So the Shannon-Nyquist principles really kind of form the basis for the digital revolution and are very important in all digital devices. But in the context of modern applications, they also have some limitations. So the problem is that, of course, today we want to communicate at higher and higher rates. We want to get higher and higher resolution, which means that we need to sample at higher rates. We need to actually build the hardware to accommodate higher rates, which is difficult to do. And then we have all of this digital data that we have to process, we have to store, and we have to transmit. And this creates different bottlenecks. Besides the hardware bottlenecks, if we look, for example, at medical imaging, then high rates often translate to long scanning times and high radiation dosage. So these ADCs, right, the going to the digital domain at the end leads to hardware, data, and power bottlenecks that we want to try and overcome. So these are limitations really coming from the engineering side or from the hardware side. We also know that we have limitations coming from the physics side. And in particular, we know that we're always limited in resolution, meaning that any measuring device will not have infinite resolution in time, space, or in frequency. And this follows from the fact of spreading of the waves, or the diffraction limit, which means that the waves spread when they pass through an aperture. So for example, if we look at optical imaging, we know that we're limited by Abba's diffraction limit, which says that we can see details that are smaller than half the wavelength used for illumination. So we'll be able to see cell and bacteria, but not proteins and small molecules. And other examples are spatial resolution, for example, when we're using an antenna array in radar and communication, or in medical imaging, like in an ultrasound probe, the spatial resolution is going to be limited by the actual physical aperture. So we see that both the science, the physics, and the math coming from the Shannon and Nyquist principles lead to different bounds on technology. And the question is if we could overcome them. So what we're going to try to get across today in the time we have is basically, if you can't beat them, join them. So each one of them alone, the math alone and the science alone, impose limitations. But what we're going to try to show today is that we can overcome them by harnessing the power of coupling the physics and the math. So basically, we're going to use the mathematical powers to suggest new ways of transmitting information that can't be heard or seen directly, but they can propagate with better resolution and more efficiently. And then we can use the algorithms to recover this information in an efficient way, even though we can't just see it directly. So it's this coupling of the math and the physics that could enable us to kind of overcome these different types of bounds. So that probably sounds rather abstract. And what I want to do next, before I kind of delve into the details, is try and give one or two examples just to make this a little bit more concrete. So let's look, for example, at ultrasound. We know that ultrasound is wave-based, and therefore it's resolution limited. So a typical ultrasound, a typical tumor in an ultrasound will look something like this. This is a tumor. This is a breast tumor, actually, in a patient's breast. And all we see here is a black hole, right? So we know there's something here, but we can't see the details of the tumor. So we don't know, for example, if it's malignant, if it's benign, if maybe it's just a cyst. Now, we can try to overcome this limitation by physics. So we could use these contrast agents that are FDA approved. These are basically microbubbles that have better reflection. So the ultrasound reflects better from them. And we could hope that the physics will help us see what we can see just with the naked eye. So we can inject these microbubbles into the bloodstream. And unfortunately, what happens is that they do indeed have better contrast, but they just make the entire image brighter. Okay, so this is what the physics gives us. It gives us better reflection, but that doesn't actually allow us to see better within the tumor. But if we combine that with good math, and what we're doing here is actually a model-based AI method, which I'll explain later on, then we see that we can actually see with very high resolution the details within this lesion. And unfortunately, in this case, we can see that this was actually a malignant mass because we see that it's very inhomogeneous. In the middle here, there's no blood vessels, and the blood vessels are all at the periphery. And we see that the shape here is very uneven, which is indicative of, unfortunately, of a malignant tumor. So this was the same image we've seen before. Okay, it's the exact same image, but this combination of the physics injecting the bubbles and then using an AI method that basically tracked those bubbles enable us to overcome this resolution limit and see within the tissue. So this is an example of combining the physics and the math in order to get better resolution. We can actually do something very similar in microscopy. So we've mentioned already the resolution limits in microscopy. And in 2014, the Nobel Prize in Chemistry went to this really clever idea of superresolution fluorescence microscopy, where we insert fluorophores into the tissue we want to image. And then instead of taking one image, we take thousands of images, where in each one, there's only a small number of fluorophores that are actually fluorescing. And then we can basically pinpoint them, sum over all images, and get one super resolved image. So this is a way to use the physics to get, or the chemistry to get better resolution. The problem is that it's at the expense of time. So instead of taking a single image, we now have to take thousands of images. And this, of course, precludes live cell imaging. But again, what we can show is by combining the two, using the concept of fluorophores, but now actually inserting them at high density and using clever AI methods, we could actually get very good resolution from only a small number of images, and therefore pave the way to live cell imaging. So hopefully this gave you some examples of how we could combine the science and the technology to come up with new ways of acquiring data, new ways of transmitting data, together with new mathematics to extract this data. And we've used this in various different applications. We already mentioned ultrasound. We've been using this for quantization, for building better devices, for better radar and communication systems. So really across a wide range of applications. And hopefully throughout the rest of the time I have, I'll be able to convince you that this could be used in many different areas. So let me continue to kind of delve into a little bit more how this kind of technology works. So the main idea is that if we look at systems today, they're really built in a very modular fashion. So basically, we design the blocks independently. The first block is always going to be the sampling. So for example, if we're looking at an ultrasound system, we transmit a signal, we get the signal back, we sample it. And here we're typically going to be limited by the Nyquist theorem. We then quantize it based on Shannon's principle. And then we do, whatever processing we need in the context of ultrasound. It might be beamforming, steering the waves to a certain direction and getting our image. But the problem here is that each of these blocks are optimized separately, and therefore they're kind of bounded by the traditional bounds that, as we've seen before, limit the technology. What we propose to do instead is to do joint design. So we're not going to join the blocks. We're not going to design the blocks independently, but instead we design them together, where in this design, we take into account several important things. So first of all, we're going to take into account any structure that we may have in the input or in the system itself. We take into account the actual output that we're interested in. And we're going to take into account the fact that I don't have to see or hear the output directly. I could rely on a mathematical recovery so that I only hear or see the proper thing after proper digital processing. So let me try to make those kind of individual elements clear. And what we'll see is that not only is this useful for designing better systems, but we could also use this in the world of AI for designing better AI mechanisms that are totally data-driven. But again, we can use these ideas to get better model-based AI methods. So let me kind of go through those elements one by one. The first thing we said is that we're going to exploit structure. So for example, if we're thinking of a radar signal, it will always have structure to it, because the way a radar works is that we send a pulse, we get reflections of this pulse, and then what we try to do is find the time of arrival, which will tell us the distance to the target, and the amplitude, which will tell us the velocity. Now, we get a very similar model in ultrasound. We send a pulse through the ultrasonic probe, and what we're viewing are reflections of this pulse as it propagates through the tissue. So standard systems don't take this structure into account. They do that only at the end in the processing. But if we take the fact that these signals all have structures, they look of streams of pulses, then we can actually get much better systems, better resolution, and more efficient hardware, as we're going to see shortly. So that's kind of how we exploit structure. How do we exploit mathematical recovery, meaning using the mathematics to get better recovery? So a good way to understand that is by looking at this issue of dynamic range. So in general, dynamic range is defined as the difference between the maximum and minimum values of the displayed signal. And we know that typically when the dynamic range is low, then the signal gets clipped. We can't see beyond a certain range. So here you see, for example, what we see when we have a narrow dynamic range, right? We don't get very, very good contrast. But on the other hand, if we have a broad dynamic range, then we can see the image much better. Now, all natural imaging devices have a dynamic range and they clip the signal. But of course, whatever is clipped, we can't resolve. So in cameras today, there's obviously different mechanisms to try and make the image look better, but it's not real information because the information got clipped. Instead, what we suggest to do is to use mathematics. So what we're going to do is we're going to use a modular operation so that anything beyond the certain area that we can see just gets folded in. So for example, if our dynamic range, let's say, is between 0 and 10, and we get a value of 12, we're just going to wrap it back to 10, okay, to 2, sorry. We're going to do a modular operation. Now, of course, what happens then is that if we take this image and do a modular operation, we're just going to get this folded image. So it looks awful. But the important thing is that all the information is there now. And if we use appropriate mathematical algorithms, if we use appropriate signal processing algorithms, then we could go ahead and recover that information. And we could do this very efficiently in hardware as well. So this is a device that we've built that we call a modular sampler. So it does this sampling in a modular fashion. And in that way, it essentially has almost infinite dynamic range. And the important thing here is that what you see at the output, which is this mess, is fine because I don't have to look directly at the output. I could look at the output after appropriate recovery algorithms. So that was an example of how we can use mathematical recovery. And what we could do at the end is basically combine the two. So we can combine the structure with the mathematical recovery to suggest more efficient hardware by changing the type of information we record. So standard sampling mechanisms record by using a clock. So there's a clock that every fixed amount of time will record the amplitude. What we do instead is we get rid of the clock, and instead we do what's called event-based sampling. So every time the integral of the signal passes a certain threshold, we record the time at which that happened. So this is a much cheaper way of building hardware. This is the hardware we built in the lab. All it needs is an integrator, a comparator, and a reset mechanism. So very, very simple on the hardware side. But by combining these principles that we've discussed before with the mathematical recovery, we can actually prove that we can recover the underlying signal. And for example, one application that we've been looking at already is using this for continuous monitoring because it's very low power. So we could continuously monitor patients by using this type of device. So putting this all together, we could develop a whole set of hardware devices that allow us to do practical compression, sampling and compression simultaneously so that we get very cheap devices that could overcome standard resolution limits in time and space and in frequency. And this could lead to a variety of interesting applications. So we've looked at, better imaging devices, fast and quantitative MRI, very efficient wideband sensing, high resolution radar, joint systems, which could do radar and communication at the same time because both of them are done efficiently, super resolution. And we can use the same ideas in totally data-driven problems to get what we call model-based AI. So getting AI methods that are no longer box, but are actually interpretable by using these types of techniques. So what I want to do in the time I have left is kind of show how we can use these principles in the context of various different applications and hopefully convince you that despite this very, very, of course, clever statement by Einstein in theory and practice are the same, in practice they are not. If we take the practice into account when we're developing the theory, then we could actually get theory that works in practice. So the first application I want to show is to ultrasound imaging. And here what we've done is we've used these principles to show that we could create an ultrasound image from very, very small amounts of data. And what that allows us to do is totally get rid of the machine. And instead of having a big machine, we can now have a small compact probe where the sampling is done directly within the probe. Today, there's no sampling in the probe. The probe is analog, the keyboard is analog, and all the sample and processing is done within the machine because of the high rates and the high power consumption. But using our methods, we can now do it very efficiently within the probe. And then what comes out of the probe is the actual raw data. Okay, so that data can now be transmitted over any Wi-Fi channel. And therefore, the doctor no longer needs a big machine. They could just have a probe and some screen, as
Hello,
we see here
everybody.
in the next demo.
I would like to show you here.
So this is Dr. Shai Taiman Yalden, a cardiologist that we've been working with.
Here
and he's scanning one of my patients using this probe that we've developed.
We can see
okay, so here you see the data is going directly from the probe to the local machine, to a remote machine through the cloud, and to a tablet.
Atrium and the right atrium. We can see the different structures of the heart. We can see the mitral valve and the tricuspid valve. We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject.
Okay, now you see the doctor scanning directly to a tablet, and as you heard him say, the resolution is very good. The other advantage we get, besides the fact that we no longer need a machine and could just use a simple probe, is that now we actually have access to the data coming back from the body, not just to the image. And we could use that in two different ways. One is to create better images. So now we could use kind of model-based AI to get a better image out of that raw data, as you can see here on this slide. And the other thing we could do, which is very interesting, and this is kind of work in progress, is that now that we have that channel data, we can actually try and map out physical properties of the tissue and not just an image. So for example, if you're looking at a tumor like we've seen before, you might see something like this. Okay, this would be a typical ultrasound image. But if we can map out the physical properties, for example, the speed of sound, then we know that the speed of sound in a tumor will be different than the speed of sound in tissue that's not tumor because of the different physical properties. So by having the channel data, we can actually, again, use model-based AI based on the physical wave propagation equations and extract these quantitative information, leading to quantitative or inverse ultrasound, which is something that today is very difficult to do. So that gives kind of hopefully a sense of how we could use this in the context of ultrasound. We could do very similar things in the context of radar. So we could get very efficient radar systems. We could get systems that could scan, broad areas at very low bit rates and very low power. And we've been using this in the context of automotive radar, where power is very important. And of course, speed is very important. We could use this for spatial arrays. So we could dilute spatial arrays using fewer antennas, which again is very important in the context of automotive radar. And here you see, for example, a demo from our lab of using a sparse array. So instead of using a full array, we only use a small number of the elements, and the other elements we're actually going to use for communication. So here you see kind of a field demo that we did at the Weizmann Institute based on these principles. All of these movies are actually available on my webpage, so you could take a closer look at them. And what you see here is a recent demo we've been working on where, because we know how to do both the radar and the communication efficiently, we can now do them jointly on the same chip. And what that allows us to do is to share information between vehicles. So, if we have a pedestrian crossing over a crosswalk, maybe one of the cars could see the pedestrian, but other cars can't. So if you could both sense and communicate very efficiently at the same time, then you're basically extending the viewing angle. And this is what we're showing here on this demo. These are kind of the two vehicles that we've built exploiting this principle. So let me take just a few minutes we have left and talk briefly about how we use this for super resolution. So we've already mentioned the problem of super resolution in optics. And here what we did is we took a very small number of frames. So rather than the 12,000 frames that are used in the method behind the Nobel Prize, we used 2 orders of magnitude less images you see here in SPARCOM and Learn SPARCOM. So this is a method based on optimization, and this is a learned version of that method. And you could see that we get very, very good resolution where we don't need to know anything about the system. We don't have to know any prior properties. And all of the training here was done on a single image. So the training here is very, very efficient because we are using model-based ideas. So now we're using this together with the group of Professor Gilad Aran for live cell imaging, now that we could do things very quickly. And for the first time, together with Gilad's group, we've been able to see cellular dynamics during T cell activation due to the fact that we could do this very quickly. I've already mentioned the ultrasound application, where we're doing something very similar by injecting these microbubbles. So that's the physics part, and then using these model-based AI algorithms to track the bubbles. So this was done together with the group of Dr. Uwe Grubstein at Billington Hospital. And here before, this is the image we've seen before, but here you see several of the images where before the processing, they all look like black holes, right? We could see the lesions, but we can't see within them. And then after the processing, we see that these lesions are actually very different. So here, unfortunately, we could see the tumor. Here we see that it's a cyst because it's basically a sac with nothing in the middle. And this shows that it's basically a benign tumor. So it has a very nice oval structure, and it's very homogeneous, which is typical for a benign type of a tumor. So I think, do I have 5 minutes left? Yeah, okay, good. So I'm going to take the next 5 minutes, just, and a lot of this we've talked about before, but just to wrap up by emphasizing more specifically how we could take these ideas to data-driven methods, which have nothing to do with the hardware we've spoken about before. So before we spoke about how we use this combination of physics and engineering in order to get better hardware, better system development, but we can also use this for totally data-driven problems, which is what I want to show next. So we all know that deep learning, of course, achieves superior performance in many different areas. There's many fields where systems based on deep learning, of course, are the best available systems. But they also come with various different limitations. So, for example, we know that we need typically very large training sets to get good results. The training could be computationally very exhaustive, so it's not relevant, for example, in communication systems when we want to do things on the edge. It's not clear how we interpret the method, so we get a result, but it's often very hard to explain it. It's not clear how well these methods generalize, how robust they are, which could be real issues if we're looking at systems where safety is a concern, like radar, automotive radar systems, UAV systems, or medical imaging systems. Now, on the other hand, when we look at signal processing, by definition, it's very model-based, right? We can incorporate anything we know about the problem, domain knowledge, structure. Typically, we could get inference from a small amount of data, and we have really nice analytical techniques to assess the quality of the output. But of course, the drawback is that it requires very accurate model knowledge, and the inference often could be quite slow. So what we want to do is basically combine, the power of model-based methods that we're used to in signal processing with deep learning. And by combining them, we could get very simple, interpretable, and simple to train data-driven systems. And you've already seen some of the results. So the question is, how do we do that, right? How do we incorporate these ideas of model together with deep learning? And we do it in two ways, inspired by everything we've seen before. The first is that we use our optimization algorithm to design the architecture of the network by deep unfolding, and I'll show that on the next slide. And the second is a more plug-in approach, where we start with our algorithm that we know works well when things are known, but then we replace any block that depends on the model by a very small, typically quite shallow network. So I'll show these two ideas, and with that, we'll wrap up. So the idea behind deep unfolding, which goes back to a really beautiful paper of Gregor and LeCun about a decade ago, but we and many others have expanded it in many ways, is to start with the model-based approach that gives us a nice optimization formulation, right? So that's kind of the physics part of it. But then what we're going to do is we're going to write down several steps of this iterative algorithm. And then each one of these steps is going to depend on parameters. This is the physics part. It depends on the physics of the problem, which in practice we may not know exactly. So in the last step, what we're going to do is we're going to free those parameters and learn them from data. And in that way, we get an architecture that's inspired by the physics, but the actual parameters are determined by learning. Okay, so those of you interested, we have a recent review we wrote on this topic, which describes these ideas and various applications in more detail. So we've seen many applications throughout the talk. Just to throw in one more, together with the group of Professor Vishal Monga, we've used this, for example, for image deblurring. So we've showed that we could compete with state-of-the-art methods that are much more complicated, are very, very deep. They train on a lot of data. And by using a simple network with just 10 layers, that's an unfolding of an optimization formulation, we actually get better results than competing methods. More recently, we've worked with the groups of Professor Ruud van Sloan and Daniel Friedman from Google to not only do the learning of the architecture, but also to learn the prior as well. And this further increases the ability of the method to learn from data, but it still is an interpretable method. We've used this for COVID detection, where we incorporate learning by the fact that there's a lot of knowledge we know about the lungs, and we were able to get very good COVID detections from small amount of data, both from X-ray and from ultrasound. We've used this to do separation, for example, in ultrasound imaging, separating the blood flow from the tissue, or separation in radar, for example. So let me skip that. So these are all ideas that are based on optimization and using the physics to kind of determine the architecture. The second approach is to actually start from the method itself, when we have methods that are reliable and work well, but then take any block that depends on the model and simply replace it by a network that only learns that block. So instead of doing end-to-end learning and replacing everything by a network, we're only replacing the specific block that has things that we may not know. And we've been using this a lot in communication systems. So again, those of you interested, we have a recent review on this approach as well. And just as one example, and this is work that we did together with the group of Professor Andrea Goldsmith from Princeton, is we've used this to develop what we call ViTurbiNet, which is basically a Viterbi algorithm over unknown channels. So what we do is we keep the Viterbi structure. So Viterbi basically computes a likelihood and then does dynamic programming over the trellis. Instead of replacing this by a network, we keep the trellis because that works well. And the only thing we need to learn if we don't know the channel is the likelihood itself. So we learn the likelihood and plug it into the rest of the Viterbi algorithm. This actually seems super trivial. And in fact, it gives amazing results with very little training data, but this is not what people do today. So today people typically just do end-to-end learning. And what we're showing here is that, again, preserving the structure actually gives us much better performance from much less training data and adapts better to changing environments. So with that, let me wrap up, hopefully on time. So we've discussed how we could try and couple physics and algorithms to learn more from less data. We've discussed how we should exploit end-to-end structure in both model-based and data-driven methods. We've seen that this leads to new mathematical and physical limits on superresolution, coding rates, and sampling rates. We've seen that it could lead to interesting new engineering devices. We could get new samplers, new technology applications that basically break existing barriers. And to us, one of the interesting things moving forward that we're very excited about collaborating on, if anyone here is interested, is seeing how we could get future scientific or clinical breakthroughs now that we could see things that we couldn't see before. So with that, I'm going to end. Those of you interested, of course, in the technical details that I didn't have time to go through, you could look in our books or the papers on our webpage. And of course, none of this would have been possible without my amazing group of students and engineers that I've had the pleasure and honor to be working with. And of course, my amazing collaborators who all contributed greatly to these ideas. And thank you very much for your attention. Very happy to take questions.